All right, today we're diving into some really cool research that could totally change how we fix major bone injuries. It's a story about scientists who are figuring out how to build new bone, literally from scratch.
Okay, so just imagine this. You have a really bad fracture. I'm not talking about a simple crack, but a serious gap in a bone that your body just can't fix on its own. Now, what if instead of all the usual fixes, we could just give our bodies a kind of blueprint to rebuild that missing piece perfectly? Well, that's the big question that's pushing this science forward.
So to really get why this new stuff is such a big deal, we got to look at how we fix really bad bone breaks right now and, why those methods aren't always great.
Right now, the gold standard treatments, well, they have some pretty serious downsides. First, you've got something called an autograft. That's where doctors take bone from another part of your own body. Sounds okay, right? But it means a whole other surgery site that's going to be painful. And let's be real, you only have so much spare bone to go around. Then there's the other option, an allograft. That's bone from a donor, but with that comes the risk of your body rejecting it or even disease. So yeah, it's pretty clear we need something better.
And this is where things get really interesting. This need for a better solution brings us into the awesome world of tissue engineering. And it introduces the hero of our story today, the bone scaffold. The whole idea is, instead of borrowing bone from somewhere else, what if we could just guide the body to build its own? This is where scientists are getting super creative.
So what exactly is a bone scaffold? Well, think of it just like the scaffolding you see on a building. It's not the building itself, right? It's a temporary frame that lets the real workers, in this case your own bone cells, come in, get themselves organized, and start building new bone. And here's the best part. Once the job's done, the scaffold just disappears. It gets out of the way. But creating the perfect scaffold, it's a huge engineering challenge. I mean, look at this wish list. It has to be biocompatible, so your body doesn't freak out. It needs to be porous, kind of like a sponge, so cells can move in and get nutrients. It's got to be strong enough to take some weight, and on top of all that, it has to be biodegradable, meaning it dissolves at just the right speed as new bone grows in. It's a massive, massive puzzle for materials scientists to solve.
So, how did the researchers in this particular study try to solve that puzzle? Well, they started with a pretty clever base recipe, and then they added a secret ingredient, something they hoped would give it a real kick.
Okay, so the base recipe is this really smart mix of three things. First up, Chitosan. It's a natural polymer that comes from the shells of things like crabs and shrimp. And it's great because the body doesn't reject it. Then you've got gelatin, which is fantastic for helping cells latch on and feel right at home. And finally, they add something called PVA, which is a synthetic polymer that gives the whole thing some much-needed strength and toughness. And now for that secret ingredient. It's a compound called Ipriflavone. Now, you might have heard of it as a supplement that people sometimes take to help prevent bone loss, like with osteoporosis. And this is what led the researchers to this really brilliant idea. They thought, wait a minute, if this stuff can help stop bone from breaking down, what if we put it directly into the scaffold? Could it actually kickstart and encourage new bone to grow?
Okay, so the recipe was locked in. It was time to put this new material through its paces, a whole series of tough tests to see if it could really do what they hoped it would.
All right, so let's meet the contenders in this little scientific showdown. On the left, you've got F1. That's just the basic scaffold, no fancy extras. In the middle, we have F1IP. That's our challenger, the one loaded up with Ipriflavone. And on the right, there's F1HA. This one has something called hydroxyapatite, which is a pretty standard material used in bone repair. Think of it as the control group or the benchmark they have to be. First up, the strength test. Basically, how much pressure can these things handle before they break? The base scaffold, F1, comes in at about 19.5 megapascals. But get this, F1IP, the one with our secret ingredient, hits over 28. That's a huge jump in strength. And this is a fantastic first sign because it shows that adding Ipriflavone didn't just have a potential biological effect, it actually made the scaffold physically tougher. That's a win.
Okay, next up is durability. And remember, the key here is that you don't want the scaffold to fall apart too fast. It needs to stick around long enough for the new bone to form. So, after 21 days, the basic scaffold had lost almost 60% of its weight. But our ipriflavone scaffold, it degraded much more slowly, losing only about 53%. That slower breakdown is exactly what you want to see. It gives those new bone cells plenty of time to do their job.
All right, so it's stronger, it's more durable, that's all great. But now we get to the real million-dollar question. Can it actually help grow new bone? This is the big one. Let's see what happened when they finally added living cells to these things.
Wow, okay, these images are just amazing. What you're looking at is the scaffolds in action over 72 hours. Each one of those little blue dots is the nucleus of a living bone cell. Now just focus on that middle column, the F1IP. Look at how the number of cells just explodes. You can physically see them attaching and multiplying way more than on the basic scaffold. It's so clear. The cells absolutely love this ipriflavone environment.
So this chart is measuring something called ALP activity. You can just think of it as a report card for how busy the bone cells are. The higher the number, the more bone-building work they're doing. And look at that. Once again, the Ipriflavone scaffold shows a really big jump in cell activity compared to the base model. This proves it's not just a nice place for cells to hang out, it's actively encouraging them to get to work.
And here it is. If you had any doubts at all, this is the visual proof we've been building up to. That bright red color you're seeing, that's from a special stain that sticks to calcium, the actual mineral that makes bone hard. Now look at the base scaffold on the left. Yeah, there's a little bit of red. But then look at the Ipriflavone scaffold on the right. It is just lit up. That is a massive amount of new bone mineral being laid down. It's the clearest sign you could ask for that this thing really, really works.
So, what does all of this mean for the future of healing? Well, the tests are done, the results are in, and honestly, the verdict is incredibly promising.
I mean, the researchers themselves put it perfectly. They concluded that ipriflavone is a really promising additive for this kind of technology. It doesn't just make the scaffolds physically stronger, it also supercharges their biological performance. And all of that leads to way better bone formation.
And this isn't just some cool experiment stuck in a lab. This tech has the potential to make a huge difference for real people. We're talking about rebuilding jawbones, fixing serious damage from gum disease, or making sure dental implants are successful. In all of those cases, being able to reliably grow new bone isn't just a nice to have, it is absolutely critical.
Really, what we're witnessing here is a move away from one-size-fits-all solutions and toward truly personalized medicine. This research is a huge step in that direction, and it leaves you with a pretty exciting thought, doesn't it? How long will it be until a doctor can custom design and 3D print the perfect scaffold just for you, loaded with exactly the right ingredients to heal your specific injury? The future of healing is literally being built, one tiny scaffold at a time.